Hi, welcome back. Today we have a question. A wind turbine with a rotor diameter of 50 meter and it is exposed to a 60 kilometer per hour wind at standard atmospheric conditions, 100 kilopascal and 25 degrees Celsius. Calculate the following: A. Available wind power. B. Maximum power that can be obtained from the wind. And C. Maximum torque if the turbine rotate at 40 rpm. So the first we need to analyze the question. What the question asks? This one, calculate the available wind power. This is the power input from the wind. And then the maximum power. And then the maximum torque if it rotate at 40 rpm. Okay, so the first step we solve A first. Step 1. Okay, in order to calculate the available wind power, right, we must know that the wind power is actually equal to the wind the power input from the turbine. So it is coming from the fluid. So basically the turbine receive energy from the kinetic energy. So the kinetic energy is energy related to half mv squared. Alright, in order to convert the energy into power, we know that E, okay, in order to convert this, we have to divide this with time. We know that energy equal to power E equal to PT. Okay, power multiply with time. In order to get power, energy over time. So we have to divide all this with time. So energy divided with time, we got the power in terms of W dot equal to 1 over 2 M. Mass we divide with time, we got mass flow rate V squared. We know that mass flow rate is actually equal to rho AV. So we shall replace mass flow rate V in terms of rho AV. So 1 over 2 replace with rho AV multiply with V squared. You simplify, you will get 1 over 2 rho A V cube. Alright, this is the power input from the wind turbine. So step number 2. Okay, step number 2. We need to get the density of the air here given at the atmospheric condition. So by using the ideal gas equation, PV, okay, equal to mRT, pressure, volume, mass, gas constant time temperature. Alright, so in this case, the R of the air refer to 287. Okay, there are some parameter. If we use R, when this equation we use R of air 287. Okay, joule. This is actually joule per kilogram Kelvin. If you use this formula, PV equal to nRT, you have to use different R. R refer to 8.314 joule per mole Kelvin. Alright, so in this case, we are not using this one. We are using this one. So we use the R 287. So in order to get the density, volume move to the other side. become division mass over volume RT. So equal to mass over volume is density. Density RT. So let's make density here become the subject. Thus pressure over RT. So what's the pressure condition? The pressure is 100 kilopascal. Alright. So 100 kilopascal in terms of 10 to the power of 3 over R is 287. The temperature make sure in Kelvin. So the temperature is 25. So 25 convert to Kelvin plus 273. Thus, the density given here is 1.17 kilogram per meter cubic. So we find the density. And then we need to find the velocity from continuity equation. So step number 3. Apply continuity equation which is mass flow rate equal to rho A V. Okay, given here the mass here. Okay. Okay, once it is not given the mass flow rate, well, basically we don't have to apply the continuity equation because we don't have any mass flow rate or volume flow rate. But here it is given directly the velocity. Right, the velocity to be 16 km per hour. This is not SI unit, alright? So based on the velocity given, we have the density and the area to be given the diameter 50 meter. We can use the cross-sectional area. So the work, the power from the fluid given here previously is 1 over 2 rho A V cube. And we know that area is pi r squared. So pi multiply with radius. Radius here is 25. Because this is diameter. So 25 squared. So you will get the area to be pi multiply with 25 squared. So you will get 1963.5 meter squared. Alright, so based on this one, straight away include substitute in this equation. 1 over 2 rho is 1.17, area is 1963.5, and the velocity here is 16 km per hour. So convert this velocity first to SI unit. 16 km per hour. Convert this. Alright. And then you will get 16 times 10 to the power of 3 over 360. 3600 seconds. So this is how you convert into the SI unit. Okay. You will get 16. You will get 4.44 meter per second. Right? So just substitute here. 4.44 meter per second, the power of 3. So the final answer for power input from the air or from the fluid is 103 kilowatt. Alright, so now we have found the available wind power. So how to capture the power, the maximum power that can be obtained from the wind. So we previously have the formula to find the theoretical maximum power from the wind. We must multiply with the efficiency of maximum. So here, step number 4. Okay, in order to get the maximum power obtained from the wind, we use this simple formula. W dot max equal to efficiency of max multiply with available wind power that we discover this one, which is W. So this is to be constant, fixed here, 0.593. So 0.593 multiply with 103 kilowatt. So the answer is 61.1 kilowatt. This is the maximum that we can get from the wind input turbine. Okay, and lastly, the maximum torque if the turbine rotate at 40 RPM, right? So this is step number 5. In order to get the maximum torque, we use the maximum power output. Alright, the formula is this. Use the formula of W dot max equal to 2 pi n multiply with torque. Okay, in order to get torque, W max over 2 pi n. And make sure n here is in terms of, okay, in terms of RPS. Alright, radian per seconds. Okay, so here it is given that it is rotated at RPM. Okay, revolutions or revolution per minute. We need to convert to radians, or we call as radian per second. Okay, so here W max given here is 61.1 kilowatt multiply with 10 the power of 3 over with 2 pi. Here, the n here. N given is 40. Okay. 14 RPM. Revolutions. Okay. Sorry. RPM is radian. Sorry, radian. Rad per minute, RPM. So we need to convert this 1 minute over 16 seconds. Okay, you solve this, finally you will get the answer is 14,600 Newton. Okay, 14,600 Newton meter of maximum torque. That's it.